Hello everybody, welcome back to the cumulative review number 14. We're going to start here with number 6. Use the graph to answer each question. Use infinity, negative infinity, or DNE where appropriate. So the first thing we want to do is find f of 0. So we're trying to find the exact y value at 0. So if I look at my x value of 0, the y value that exists there is also 0. So because it's at the point 0, 0. What is the y value that actually exists at 2? Well, 2 is a vertical asymptote, so there are no actual y values that exist. So this one will be DNE. F of 3 will be at the value 1, 2, 3, at the x value of 3. Even though there's not a point there, it crosses the x-axis again. So this answer would also be 0. Part D, find the limit as x approaches negative 1. And again, it does not have a direction, so that means you need to look from both directions. As we're looking As we're approaching negative 1 from the left side, the graph goes up towards positive infinity. And as we approach the x value negative 1 from the right side, the graph goes down to negative infinity. So because the limits are not the same from left and right, this limit does not exist. If we look at part E, limit as x approaches 0, again, we need to look from both sides. As we approach the graph from the left, it's approaching 0. As the graph is approaching from the right, the x value of 0, it's also approaching 0. So because the limits are the same from the left and the right, and they're both 0, this answer has to be 0. Next, we want to find the limit as x approaches 2 plus, so 2 from the right side. So if we're looking at the x value of 2 from the right side, the graph here is from the right because it's going down towards negative infinity. So two answers will be accepted here, either negative infinity or technically, because negative infinity is not really a y value, DNE is also an appropriate answer. Last but not least, find the limit as x approaches infinity. So we are now, as the graph goes forever towards the right or towards negative infinity, this right here represents a horizontal asymptote at y equals 1. So the graph, if it keeps going towards infinity, is going to approach but never hit the y value of 1, which means the limit has to be 1. Number 7, evaluate. So again, here we go. We have log, log, and log. Remember that logs are exponents. So all of your answers to these problems should be exponents. And so what you could do is think of these as little equations. We don't know the exponent, but we know the base is 3. We don't know this, but we know the answer should be 81. So 3 to what power equals 81? Why, that's the 4th power. So my answer is just the answer of 4. Part B, we know the base is 2. We don't know the exponent, but we know it should be equal to 1/8. Well, I know that 2 to the 3rd is 8. And so what type of exponent, again, causes a reciprocal? A negative exponent. 2 to the negative 3rd is really 1 over 2 to the 3rd, which is 1/8. So the exponent that I want is negative 3. Part C, the base is 5. Don't know the exponent, but I know it should equal 1. Any base to what power equals 1 every time? 0. Anything to the 0th power is always 1. Part 8A and B, condense the logarithmic expression to a single logarithm. So we only want one log or one ln. And so when we want to condense, we want to move all numbers up to exponents, and we want to make it one single log. So if I was looking at part A, the first thing I would do is move the 3 up as an exponent. I would move the 2 up as an exponent as well. And I would also move the 1/2 up as an exponent. And what we can do is simplify this a little bit, because 2 to the 3rd is really 8. So this is ln of 8 plus ln of 3 squared, 9, minus ln of 4 to the 1/2. Remember, 1/2 really, or to the 1/2 means square root. So we're really thinking square root of 4, which is really 2. So we did a little simplifying, but we still don't have a single logarithm yet. So what I know is that if I'm adding two logs and I'd like to make this into a single log, you can really take the two separate logs added and multiply the arguments to make it into a single log. but we still have this minus ln2. So I have ln of 72 minus ln of 2. If I would like to combine these two logs, if I'm subtracting two separate logs, that is the same as a single log with the arguments being divided. So that is how the final answer is ln of 36. Now, some of you at this step right here may not need to do it in two steps. Some of you may recognize right here that if you're adding two separate logs, the 8 times 9 will be on the top. If you're subtracting the ln2, the 2 would go on the bottom, and you can more quickly get to ln of 36. I took it in steps just for those that it might help. Part B, we again want to get this to a single logarithm. So let's move all exponents up if applicable. This one has a 1, so I'm just going to leave that the same. I'm going to make this one log base y, or log base 10 technically, y to the 7th power, minus log of z to the 1/2 power. Now, this is similar to something that we did in class. If we have a log minus and then minus, this can be a little confusing because unlike this example, when we added, we knew those would be on the top and then this only would be on the bottom. Some of you might look at this and say, I know both of these need to be on the bottom. But to help understanding, you can think of this problem as subtracting log y to the 7th plus log z to the 1/2. Because if you took the negative out of both, you would have minus something being added. The reason this is nice is now you can think of it as a log minus another log. So again, what we could do is combine these two to become, so if we kept this the same again, log of x minus, these two, because they're being added, could become log of y to the 7th times z to the 1/2 power. Because when they're adding separate logs, that's the same as a single log with the arguments being multiplied. And now that I have a log minus another log, I know that it's one single log with the x in the numerator and the y to the 7th times z to the 1/2 in the denominator. So this is a single log, so it seems like this could be the final answer, but a lot of the times you see the final answer written as this instead, x over y to the 7th square root of z. To completely condense it, a lot of the times the 1/2 has changed it back to the square root. So this would be my answer for part B. Going the other way, expanding the log expressions. So now we're starting with something that we end with in part B, and we're trying to expand it. So because these two logs are in the numerator, we know they're being added. So it'll be ln of a squared plus ln of b, but because the cube root of c is in the denominator, that will be minus ln of the cube root of c. And yes, these could have parentheses around them as well if you wanted them to. So now, if you're continuing to expand, you want to bring all the exponents down in front. So we'd have 2 ln of a plus ln of b. Now this one's interesting because right now it's ln, and if you wrote this as a fractional exponent instead, that'd be c to the 1/3. So if I bring that down, we'd have 2 ln a plus ln b minus 1/3 ln c. Completely expanded. Part B. We have two arguments inside that are being multiplied. So that really means you have two separate logs, log base 3 this time, being added. Now, ln technically has a base of e. This one has a log base 3. So just make sure to carry that along with it. So log base 3 of the square root of x. If you want to complete expanding this, we would first, what I'm going to do, log base 3 of z to the 4th plus log base 3 of x to the 1/2 power. I then am going to bring my exponents in front. So I'd have 4 log base 3 of z plus 1/2 log base 3 of x. Final answer expanded. 10, rewrite log of x equals 2 in exponential form. So to rewrite it in exponential form, we need to think about what the base is, and we need to think about what the exponent is. Remember, logs equal exponents. So this number has to be the exponent. And when I see a log just on its own, I assume that it's base 10. So to rewrite this in exponential form, my base is 10, my exponent must be 2, and that must equal x. So that would be my rewritten rule there. Number 11, rewrite in log form. Because my base is e, we usually use ln with that. You could say log base e, but a lot of the times we do say ln. So I'll start with log base e, but then I'll change it. So if we want to rewrite this, we have log base e. I know that my exponent from the original is x, so it'd be log base e of 8 equals x, but this is more commonly written as ln 8 equals x. Last but not least, number 11. Find the following information and graph at least 2 points of this exponential function. Please consider the parent function first and then the transformations. So what I would do to graph this is, again, think about the most basic function that you have, or the parent function. There are some transformations that do occur, which if you see x minus 1 really means eventually we're going to be moving this right 1 and up 3. But the most basic version of this graph is just y equals 2 to the x, because we're not doing any transformations. So what I would do is make a table for the parent graph and then shift all of those points around. So again, I'm just going to pick, it says at least 2 points, so I'm going to do, I'll just do 5 because I want to be thorough here. So if I took -2 and I plugged it in here, 2 to the -2 it makes a reciprocal, so that's really 1/4. 2 to the -1st, if 2 to the 1st is 2, the reciprocal would be 1/2. 2 to the 0th is 1, 2 to the 1st is 2, and 2 to the 2nd is 4. So here are all my original points, -2 1/4, -1 1/2, and so on. But what I want to do is think about these transformations. And so in green over here, I'll make all those changes. So for all of these, if I'm going right 1, we'd get -1, we'd get 0, we would get 1, we would get 2, and then we would get 3. And if we're going up 3 from all these values, 1/4 is really 0.25, so we'd have 3.25, we would have 3.5, 4, 5, and 7. And so these are the points that we would graph before we answer any questions. So -1, 3.25, 0, 3.5, 1, 4, 2, 5, and then 3, 7. So my graph exponentially does have an asymptote, and it looks like it is decreasing and that it is going to horizontally get really close to the line y equals 3. So that's how I'm going to draw it. Exponential graphs always have horizontal asymptotes, and I'm going to draw that in right here. So if I look at my picture now, my domain from left to right would be -infinity to +infinity. Left to right. My range bottom to top. The lowest value you're possibly reaching, probably not because it's an asymptote, would be 3. That's why I have a parenthesis, because I'm not really reaching it, all the way to infinity. The line I'm not crossing is y equals 3, which means I have a horizontal asymptote. And in terms of intercepts, I do not have any x-intercepts because this graph never crosses the x-axis, but I do have a y-intercept, and I have it in my graph right here at 0, 3.5. So for your test for both exponential and log graphs, please always consider the parent function first, find those values, and then think about the transformations, especially since that relates so much to what we did first semester. All right, guys, thank you.